Welcome to Advanced Data Analysis 1 with me, Erik Erhardt, Professor of Statistics at the University of New Mexico. In this video, I'll help get you started with Class 24, Binomial and Multinomial Hypothesis Testing, and this will be an introduction which uses its own data set rather than the data set from your project. So we'll scroll down to Class 24. It has its own markdown and data files, and so we will save these to our class folder. Read the markdown file into RStudio. And knit it. We'll also set the working directory to the source file location in case we're going to do some work in the console. Oh, that's happens sometimes. We'll try knitting it again. I don't know if any of you are getting that error. Sometimes I try to knit it, and I get this error that it could not write. It creates the markdown file, which is the output from the R markdown file, but then it has trouble writing the HTML effectively. But I find if I knit it again, it works. It's possible that it's a conflict with Dropbox. This is the first time I've had to do more than 2 knits for this to work. There it goes. All right. All right, so we're going to look at data from the World Series. As I introduce, so I'm someone who grew up playing sports. I don't have anything against sports. I think it's pretty fun to play. But I do introduce this in this way. One form of sports ball is a game of baseball, and its championship, played exclusively in North America, is called the World Series. We want to answer the question, how well does the distribution of number of games played during the Baseball World Series follow the expected distribution? This is a multinomial goodness of fit test, and there are 4 categories for the number of games. Given that World Series in almost every year is a best out of 7 series, the number of games played in the World Series can end in 4 games if one team wins every game, or it could be 5, 6, or 7. Right? You get to 7 if both teams have each won 3 games, and then there's the last tiebreaker at 7 games. And we want to know whether the observed number of games follows what we would expect the number of games to be. All right. So first we're going to calculate the observed frequencies and proportions, and then we'll do the expected based on a set of modeling assumptions. The World Series, if you go to this link for the World Series, it brings you to the Wikipedia page, which has a long table of the World Series results. Blue and pink tell you whether it's the National or American leagues, also strangely named. And the winning team is in this first column, losing team is over on the right, and in the middle is the number of games that were played in order to win the World Series. And there are non-standard numbers of games, especially in these early World Series, before, as the rules settled down and converged to something that we know today. So, for example, this first World Series ended with 5-3, and which is 8 games. So what we want to do is we want to read this table, look at the games column, and we want to add those 2 numbers together. Now those 2 numbers are in a string, 5-3. It's not a number, it's a string. So we need to first separate these 2 numbers by the hyphen in the middle, break it into 2 separate numbers, and then add them together. And that's what this next piece of code does. Okay, so we attach the tidyverse. Then we're going to create an object called the data for the Major League Baseball World Series. We read in the World Series CSV file. I skip the first row. I forget what's in there, but we skip it. Then I separate the games column into two separate columns, G1 and G2. And that's where the numbers are going to go. So 5 is going to go into G1 and 3 is going to go into G2. And the separator is the hyphen. And that's this part here, sep equals hyphen. And convert, I forget what this does. I think it converts the data type into numeric. After we have created these two new columns, then we're going to mutate to create a new column called n games for the number of games, and we're going to add those games together. And finally, because in some of these early years we had best of 9 series, we are going to simply truncate that to 7. So if the number of games is greater than 7, like 8 or 9, then we're going to just say that there's 7. Otherwise, we're going to keep the number of games that was there. And there are much better ways of doing this. For example, we could go to each of these years, see what the sequence of games are. The first one that got to 4 wins, we could use that value. But quite honestly, first, I don't care. Second, it's only 4 out of maybe 100 or so years of data, maybe almost 115 years or so of data. So it seems like this is going to impact us very little. If this was, of course, if this was my research project and this was important to get right, I would get it right. But this is a case where a shortcut is just fine for us. Finally, there are a couple years when we have NAs for the number of games. In particular, after the first year, they quickly took a break and didn't have a World Series. And then there was a year when there was a players' strike, 1994, and so there was no World Series that year. Oops. So we drop those rows where the end games were NA. All right, so we read the data set in, and this is what it looks like. Notice that the games column is gone and has been replaced with the G1 and G2 columns, which are both integers, and we could add those together to get the number of games column, which is not shown here because of it was truncated due to the width. But it does say that there are 3 more variables in this tibble, and the last one is the one that we created. All right. Let's take a look at the observed data. I've gone ahead and plotted it here. I've put year along the horizontal axis, the number of games along the vertical axis, and if you want to connect these dots with a line, you can uncomment this. I thought it was a little bit noisy. But you can see as we go through, there's lots of years that go to all the way to 7 games, and fewer years that either end in 4, 5, or 6 games. We can calculate the proportion of the number of games ending in each of the 4, 5, 6, or 7 total games categories, and also calculate the observed proportions. So we're going to start with our data set, and we're going to create a new object called dat games. We're going to group by the number of games. So we're going to group it by 4, 5, 6, and 7. For each of those categories, we're going to calculate the total number of rows for that category and put that into the observed games. That's the number of games we saw that end in 4, or total number of series, a World Series that end in 4 games, and 5 games in 6 and 7. And we take that observed games, and we're going to calculate a fraction, the number of games divided by the total of all types of series where it ends in 4, 5, or 6, or 7, and put that into the observed proportion. I'm rounding it here to 3 decimal places because that's plenty. And then setting the number of games to a factor variable because that's slightly more convenient for plotting. And we've put it down here. Here's the result. So for the number of games 4, 5, 6, and 7 within a World Series, this is the observed number of games that we saw, and so there's about 20 in each of these, and then 40 that end in 7 games. And the proportions, because we have about 100 games, are similar. So we have about 20% of World Series endings in 4, 5, and 6 games, and about 40% ending in 7 games. Now, to do a hypothesis test, we need to compare these proportions to a distribution from a certain model. And we are going to make some assumptions about what games, teams playing in a World Series, and what the result could possibly be. So, under the assumption that the probability of a particular team winning a single game, right? So we're going to specify a certain probability of winning. We can calculate the probability of the World Series ending in 4, 5, 6, or 7 games, and therefore we can calculate the expected number of World Series ending with each number of games, and then perform a hypothesis test. So below, set your own probability of a particular team winning each game. So my assumption here is that on average, one team is a little better than the other. And this number, the 0.6, should reflect a slight advantage of the team with superior ability. So for example, this 0.6 means that the superior team has a per game probability of winning of 0.6, and the inferior team has the inverse of that, 0.4. And so some of the assumptions I'm making is that for every World Series, for every year of World Series, the superior team has a certain probability of winning. And within a World Series, this probability does not change from game to game. Okay, so that you have the same probability of winning every game over every year. Now, it's a very simplified assumption. But if you make that assumption, we can test whether the data are consistent with that assumption. And if they are, that suggests maybe this is a fairly good model for the number of games. And if not, that says that this is not a very good model. And in fact, another model should be devised to try to explain the data that we see. Okay. So what I've done here is, so you should set this to a number that makes sense for you. I recommend not choosing 0.6 because it will look like you did not do anything. Okay, but this number should probably be somewhat close to 0.5 because you're getting the 2 best teams from the 2 leagues in the country, and I would think that they would be generally pretty closely matched. So I would say that numbers here should be somewhere between 0.5 and 0.7, right? A team, you would be unlikely to see the probability of one team being 0.9 to a 0.1 for the other team. That would say that one league is very superior to the other league. That may in fact be true, but I don't know that to be true. So I'm going to assume that the 2 leagues are roughly equal skill. We're going to calculate the expected proportion for each number of games within a World Series. So these 4, 1 to 4 here, represent the probability of ending in 4 games, the probability of ending in 5 games, the probability of ending in 6, and the probability of ending in 7 games. And I'm going to use the negative binomial distribution to calculate the probability of winning in a certain number of games. Now, there's all these cool distributions in statistics and probability, and negative binomial distribution models the probability of ending in a certain number of trials in order to get a given number of successes. So a simple example is what's the probability, say you're rolling a die and you want to roll the die until you get 3 1s. Okay, so I roll the die, I get a 2, I roll the die, I get a 1. Okay, there's 1, 1. Roll the die again, I get another 1. That's 2 1s. Roll the die again, I get a 6. I roll the die again, I get a 5. Roll the die again, I get a 3. Roll the die again, I get a 1. There's my 3 1s. How many times did I roll? What's the probability of rolling that many times? Okay, that's the scenario. So this is the probability of rolling a certain number of times in order to get a certain number of successes. And there's a few ways of parameterizing this. This is basically saying that I need to get 4 successes, and this is the 0 here is the number of additional rolls that you need to get those 4 successes. Okay, so this first term is what is the probability that of if each success has a probability of 0.6, and what's the probability that you win every time? Win, 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 right? You get those 4 successes, and you didn't need any additional games, so you only needed 4 games. What's that probability? In fact, let's just go ahead and take this down into the console of R and see what this calculates. So here's the probability of 0.6. The probability of this superior team winning every game, 1, 2, 3, 4, is about 13%. Now the other term here is that they could get unlucky, and actually the inferior team could have won all 4 games. So this is 1 minus 0.6, so 0.4. That's the probability of the inferior team winning. What's the probability that they win all 4 games and you didn't need any additional games? So let's take a quick look at that one. About 3%. So it's much more likely for the superior team to win than the inferior team to win if it's a blowout, all 4 games in a row. And so that accounts for about 15% or so, 15.5%. And so that's what goes into here. Okay, so we do that for each number of games, right? So here is P. I always get stuck here. P and binom. So within R, you can generate lots of statistics. And so D is the density function, this prefix, right? So n binom is the negative binomial distribution. Then there's a D, a P, a Q, and R for random numbers. So we've got the density function. So that's the probability of a particular event happening. We have the distribution function, which is called the CDF, the cumulative distribution function. And then we have the quantile function, which is you put in a probability and it tells you the value of the random variable. I'm talking about things we haven't really covered in class. But the point is that I'm just double checking that I calculated this right. All right. So this is the probability of needing 1 additional game minus basically the probability of needing. Okay, so the P here, sorry, this is getting in the weeds. This is correct. What this is the P here refers to the second line here, which is the distribution function, which is the cumulative distribution function, which means that the value that this returns is basically the left tail, the cumulative distribution. So this will give us the probability of needing 1 additional game and 0 additional games. It'll give you the sum of those 2 probabilities. So if I've got both of them in here, then I need to subtract off the 0, which was accounted for in this previous line. Anyway, so the result of this is that this gives us the probability of winning only 1 game, or needing only 1 additional game to win the World Series. So that means the winning team, in this case the superior team, maybe won 2 games, then the inferior team won a game, and then the superior team won 2 more games for a total of 5 games with the superior team winning. The second set of parentheses is for the inferior team winning. Okay, and then we've got 6 games and then 7 games. Okay, so anyway, we perform all those calculations. We find that the sum of the expected proportions equals 1, which is good. We've accounted for basically the entire sample space. And we can also from there calculate the expected number of games. Observed games times, I think this should be the sum of the observed games. There's something that's not quite right here. Okay, so I think I do need to make a quick correction. Anyway, I will continue, and your version will have a correction here. The idea is that we have just created this expected proportions column, and look at this distribution. So it's 15%, about 27, 30%, and then 28. Okay, so that distribution of expected proportions is quite a bit different than the observed proportions. So perhaps the model that I've just proposed does not follow what actually happens in gameplay. Yeah, these expected number of games are not even close. Fortunately, that's not actually an important number. But this should be the total number of observed games multiplied by the expected proportions. That way, we could compare the expected games to the observed games. In fact, let me just make this correction very quickly. Let's see how the sausage is made here a little bit. I think I can just do that and get that to be correct. All right, so the goodness of fit test, sort of continuing. There we go. Okay, so these numbers have been corrected, and this this is how many expected. Given that we've played, I still don't know what this number is, 115 World Series or something. We would have expected about 18 of them to end with 4 games. We would have expected about 31 of them to end with 5 games, and so on. Okay, and this is what we actually observed. So by eye, the observed and the expected number of games, or the proportions, is sort of equivalent to compare each of those. They seem a bit different. So I think that we're going to end up rejecting a null hypothesis here, but we'll see. All right, so the goodness of fit test, we've set up the observed and the expected frequencies, and now we can perform the goodness of fit test. So every hypothesis test has the same structure. So we're going to first set this up in words and notation, and we can refer to the lecture notes in order to do this. And we're going to set the significance level, and let's just use 0.05 to be consistent with standard practice. We're going to perform our hypothesis test. So we put into a vector the number of observed games as a list. Okay, so this right here has, well, I don't think I've run enough code yet. Let's see, I can run everything down to that piece of code. There we go. So this observed game has these 4 numbers in it, that column of observed games. The proportions, are the expected proportion of games. And this correct equals false is asking whether or not we should use a continuity correction. Typically we would say yes. The reason I'm saying no or false in this case is because we want to get values that are basically consistent with what you could calculate by hand. if you wanted to practice calculating this by hand. So we get a chi-square statistic of just over 9 with 3 degrees of freedom. That is, the number of degrees of freedom is 1 fewer than the number of categories we had. So we had 4 categories. The games could either end with 4, 5, 6, or 7. Degrees of freedom is 3, and this gives us a p-value that's rather small. So we compute the test statistic. That's the chi-square value here, and you can use the names X summary to put that value in there right there. In fact, let's take a look at, let's run this and look at names of the X summary. I call it X summary because X is sort of like the letter chi, so the chi-square summary. And it looks like there's a value called statistic, and there's the number 9. And so you could print that value right in here. Similarly, compute the p-value. We have that up here as well, right here. Okay. P.value. There it is. So you can use those two values the way we've done in previous assignments to put them where they belong. And then based on the p-value and the alpha level, you either reject or fail to reject. So you can state which one of these is true, or your conclusion. And then we want to check assumptions. Okay? I think I'm reminding myself whether or not I have assumptions here. I do not. I think the assumptions is that we need at least 5 expected frequencies for every category. Okay, so if you have at least 5 for all the expected games, then the model assumptions should be met. All right. The second part of this assignment is to understand the deviations, and that's where a chi-square statistic, or the residual, comes in handy. So from the chi-square summary, there's a bunch of these other statistics. In fact, let's go back over here for a moment. You can see there's the observed value, the expected values, the residuals, which are the Pearson residuals, and also some either standardized or studentized residuals. I think these are standardized residuals. And we can use those to help get some more information. So I've got residuals and I've got residuals squared. Recall from the notes that when for the residuals squared, when you add those up, you get the chi-square statistic. Okay. All right, so we're going to put these statistics into a table, and here's the table. Okay, there's the chi-square, here's the residuals, and you can either use the residuals or the studentized or the standardized residuals. And let's take a look. I've got some comments here. So I'm going to plot the observed versus the expected value to help identify the number of games grouped that deviate the most. And I shouldn't do this right here, but I did change the notation. Plot the contribution to the chi-square values to help identify the number of games grouped that deviates the most. The term contribution to chi-square refers to the values of this quantity, right? So this is the quantity, the observed minus expected squared divided by expected. That is the chi-square statistic that you add up. And that is the chi-square, well, the residual squared. That residual is this for each cell. And when you add those up, then you get the total chi-squared statistic. Okay? You'll remember that from the notes, that you typically see this with a summation sign in front. There's one more typo here. Oh, it's not a typo. It just doesn't end up looking correct. Oh, it's because of this. Because I have strange quote marks. Okay. So I'm going to create a long version of the table, which for each number of games, so 4, I've got a statistic, which is either observed or expected, and I have the value. 21 is the observed, and 17.8 is the expected. This pivot longer is a way of going from wide data format to long data format. Previously, like in older versions of R, we would use the reshape or reshape2 package, and there was a function called melt and cast. Melt would go from a wide format to a long format, so that is what you may have seen in the notes. However, modern usage is pivot longer. And so now we can use the statistic to group our observed or expected values together, but to color them or to connect them with lines. And the value is what we're going to plot on the y-axis, and the number of games is what we can plot on the x-axis. So down here, we've got this table. We're plotting the number of games on the x, and our statistic is the fill color, and we're going to weight it by this value, and we're going to get these bars. I'm also plotting the chi-square statistic. We'll take a look at that sort of separately. So on the left are our expected number of games is the red, and what we observed is the blue. And they're quite a bit different. How different? Well, that's what the contribution to the chi-square statistic tells us. Now, if you add up these 4 bars, right? So this first bar is about 4.5. This one's a little over 3. Each of these are slightly less than 1. You'll get the 9 point something, which is the chi-square statistic. What I've done is I'm plotting the number of games is x versus the chi-square statistic. But I want to plot them in the order where the largest chi-square statistic is the first one, so that we have this decreasing relationship. So we can see that it's the difference, the deviation between the observed and expected for 7 games is the largest contributor to where our model seems to not match the data. Second is for 6 games. There's a large deviation there. For 5 and the 4 games, those are much less. They contribute much less to the chi-square statistic. And the way I've done that is you can use a reorder right here in the aesthetic. I'm going to plot number of games on the x-axis, but I'm going to reorder them based on another value. In this case, I'm ordering them by the chi-square statistic, and I do a negative chi-square statistic, so I order them in the descending order. So the largest value will be the first one, and that's what we see. So I really like this type of plot, especially when there's many categories. If there's 10 or 20 categories, you really just want to focus on the 4 or 5 big contributors. Reordering the axis is a really great idea. All right, I'm just looking to see if there's. It looks like I don't have any questions associated with those deviations, but it's a good thing to have it plotted and to understand. All right, the last part of this assignment is to perform multiple comparisons. So if, like me, you perform the hypothesis test and you rejected the null that the data follows our proposed multinomial distribution model, if you reject that, then we need to understand what part of the model was cause for the rejection. Okay, so as we look at this, it could be just that one of these categories was the major culprit, or maybe just two of them, right? So it seems like, for example, 6 and 7 games are quite a bit different, right? The expected has these red bars that go up and back down, and maybe the blue bars were starting to come up, but there's so many more World Series that end with 7 games than you expect that it really takes away the games that could have been 4, 5, or 6. So we want to understand statistically which of these categories were most responsible for the rejection. And we get some of that information with this chi-square statistic, okay? That these are the two large deviators, the 6 and the 7 games. But now we can do each category separately. So the goodness fit test above suggests that one of the number of games categories, and I will fix the number, at least one of the number of games category proportions for the observed number of games. Boy, I did a bad job writing this the first time. Differs from the expected number of games. So a reasonable next step in the analysis would be to separately test each of the 4 hypotheses, one for each of the categories. So our model says that the proportion of times we should have ended with 4 games is about 15.5%. The number of times ending with 5 games is 27%, and so on. And we can see which of these categories resulted in the rejection of the null hypothesis above, that all 4 of these proportions simultaneously weren't correctly specified by our model. If we use a Bonferroni comparison rate with a family-wise error rate of 0.05, then we have to divide by the number of tests we're going to perform, which is 4, and so we need p-values that are smaller than 0.0125 to reject a null hypothesis. Okay, so I'm going to use exact binomial distributions to perform these tests. And that's because the exact test is going to be better than a normal distribution approximation. So this looks a bit, is a lot here. I think it might be, well, we'll find out in a moment if it's a little easier to see in R. Well, my window doesn't quite get big enough. So let me do this. If I shrink this down, will it fit? Nope. Okay, so what I've done is I've got B for a binomial test, SUM for a summary, and then I've got 4 of them, 1, 2, 3, and 4. For each one, I'm doing a binomial test where I've got the observed number of games for the first category is here, right? So this test, in fact, we can go and look at the help for this test to remind ourselves about the syntax. For the binomial test, we put the number of successes, the number of observed successes as x, the first argument. We put the total number of trials as the second argument, and then we put the hypothesized probability of success, 0.5. We specify what type of alternative we have. These are all going to be two-sided tests. And if we wanted to calculate a confidence interval, we can also specify that here if the confidence interval probability was different than 95%. So we're going to go back over here. We've got the observed number of successes, or the observed number of World Series that ended in 4 games. Then we've got the total number of World Series that were played. And then we have the expected proportion for just 4 games, that first value. We have an alternative of two-sided, which we didn't need to specify because that's the default, but we're being very specific here, and we're making sure we're not making any mistakes. And the confidence level is going to be 1 minus 0.05 divided by 4, and that is what we have up here. Oops, for that Bonferroni correction. I've done that for each of the 4 scenarios, for 4 games, 5 games, 6 games, and 7 games, and I'm putting those all into one data frame. So I'm summarizing the p-values and the confidence intervals, putting those into a data frame. R-bind means row bind, so I've got the results for 4 game World Series, the results for 5 game World Series, and so on, binding them all together, putting that into B_sum for the summary of the binomial hypothesis tests. This actually has 3 columns. P-value is a single column, but the confidence interval has 2 columns, a lower interval and an upper interval. And I'm going to name these P-value CI lower and CI upper. So I've named that. I'm going to add some additional columns to our summaries, in particular the number of games, so we can keep track of that, the observed proportion and the expected proportion of games for each of those categories. And this last piece of code really just reorders the variables. So I'm putting the number of games first, then the observed and the expected proportions, followed by the p-value and the confidence interval. And this is our result. The number of games, 4, 5, 6, 7, the observed proportions, which we saw before, the expected proportions, which we saw before, and now we've got p-values for our hypothesis tests and confidence intervals, which we're not interpreting here, but they're here if you wanted to. The p-values here are the main column. Okay, so as we scroll down these p-values, are any of these p-values less than the Bonferroni cutoff? So that is this value here, this alpha, 0.0125. If I scroll down, 0.125, even the smallest one is not. So this is a scenario where we could reject the multinomial hypothesis of all 4 probabilities being equal to their hypothesized values simultaneously, but we have a very conservative significance level due to Bonferroni. This is the most conservative value that we could have. There are other corrections we could have used, but this one was so conservative that in fact we cannot reject any of these individual hypotheses, because this is not less than 0.0125. And the rest are all larger than that too. So that would be your conclusion. Okay? State the conclusions of the 4 hypothesis tests above. So we've got, for each hypothesis test, we've got the null hypothesis is equal to a certain value. The alternative is that that probability is not equal to a certain value. And then our conclusion, based on the p-value, either rejects the null hypothesis or fails to reject it. And in my case, where I've got the superior team's probability of winning of 0.6, I end up failing to reject all 4 of the null hypotheses. Okay. An additional thing that I've done here is I've plotted the number of games on the horizontal axis, the observed proportions on the vertical axis, but I've also put in some, let me just scroll down and we'll look at the plot. I'll zoom out a little bit. There we go. So on the horizontal axis we have 4, 5, 6, and 7 games. On the vertical axis we have the observed proportions. Actually, I should just label this proportion because we've got black dots, which are the observed proportions. So we've got black sort of close to 0.2 and then up to close to 0.4. And I've put in the black bars the error bands, which is the confidence interval for each of those individual proportions. The red are the expected proportions. Based on our multinomial model derived from a negative binomial distribution, we have these red x's, which is those expected proportions. And so we can see how the observed proportions differ from the expected proportions. The final question here is to write one or two sentences of discussion and to speculate as to why the deviations are the way they are. Okay, so this is sort of open-ended. I don't know why our model didn't work, but there's many deficiencies, obviously. Right? I mentioned this at the very beginning when we set this probability of winning. One is that this applies to, we're making the assumption that this is the probability of the superior team winning, and that's the same for every year and for every game within a year, and that there is such a thing as a superior team and an inferior team before you go into the World Series, and that those don't change. Okay. Something that I'm sort of skeptical of is, do they play 7 games because they can win? They can make a lot more money on ticket sales. I don't know what happens to the tickets for people who buy a ticket for the 7th game of a World Series and then that game is not played. Do they issue a bunch of refunds? There's quite a bit of money to be made, both for TV broadcasting rights and also for ticket sales to play all 7 games. So I don't know. Is there some incentive to, if you're ahead, to lose 1 or 2 games so that you can make more revenue? So that is the last part of this, just to speculate as to why you see these deviations. You're welcome to use some of the ones that I've discussed. You may have more insight into this than I do. But that is the end of this assignment. I hope it goes well for you. The main thing I do want to emphasize, of course, is that you are to choose your own probability of winning, and that will change all the results that follow. Okay?